So how do you balance chemical equations? It's something that's really impossible to teach. You just have to do lots and lots of examples. And you have to do so many examples that you feel comfortable balancing any equation that's thrown at you. The beauty of it is that you're always able to check your work and know if you are right by just counting up the number of atoms on each side of the reaction. So balancing chemical equations for me has always involved lots of trial and error, lots of erasing. So you might start going down a path that's leading nowhere and you have to just start over. One rule of thumb is to try to start with the most complex compound in the reaction and go from there. But every student has their own unique way of balancing chemical equations. And if you do enough examples, you will develop yours. So I just want to do several examples to show you how I do it in the hope that it will help you figure out how to balance chemical equations for yourself. Solid iron 3 oxide reacts with gaseous carbon monoxide to produce liquid iron and CO2 gas. Write the balanced chemical equation for this reaction. So here we have to translate these words into a chemical reaction. So iron 3 oxide, we can write the equation for iron 3 oxide as Fe2O3, and we know that it is a solid. I'm going to leave room for a possible coefficient before I write down the formula for carbon monoxide, and they told me that it's gaseous, so it gets a G. We are producing liquid iron and CO2 gas. So the products are liquid iron, so metals form monoatomic species, so we just put the element symbol and then it's a liquid, and then CO2 is carbon dioxide. This is how iron is isolated to produce steel, so it's a very important reaction from an industrial point of view. Now we have to balance this chemical reaction. So I want to, under the reaction arrow, I'm going to list all of the elements that are involved in this reaction. I have iron, oxygen, and carbon, and I'm going to count up the number of each I have on both sides. So I have 2 irons, I have 3, and then plus 1 is 4 oxygens and 1 carbon on the left. On the right, I have 1 iron, 2 oxygens, and 1 carbon. So it looks like the carbons are in balance, but the irons and the oxygens are out of whack. So the easiest thing to do is to look at the most complicated molecule, which is Fe2O3. Not a molecule so much as a compound. Fe2O3 has 2 irons and 3 oxygens. Well, the oxygens are kind of all over the place, but if I place a 2 here on the right side, at least I'm bringing those irons into balance. So now the only thing out of balance is going to be my oxygen. So I need to figure out how to kind of reconcile that oxygen problem. On the left side, I have 4 oxygens. On the right side, I have 2 oxygens. So I have to kind of guess and check to try to make these oxygens work out. I want to, if I place a 2 here, I get myself into trouble very quickly. Because if I place a 2 there, then I'm making 2 carbons, and I need to have a 2 here. And if I have a 2 there, then I have 2 plus 3 equals 5 oxygens on the left. So that's not going to work. I can't do it that way. I'm going to have to do something where I have an odd number of oxygens, because odd plus odd is going to give me an even number. If I place a 3 on the left side, maybe that will help me figure this out. That gives me 2 irons, 6 oxygens, and 3 carbons. So if I place then a 3 here, does that work? I still have 2 irons, but now I have 3 times 2 is 6 oxygens and 3 carbons. Check, check, check. Check, check, check. I am balanced. So you see how I did that? I did that through trial and error. And for some of them, there's really no other way to do it than by just looking at the reaction and trying different coefficients. Let's do another example. Let's balance this reaction where HCl, aqueous, plus calcium carbonate as a solid gives me solid calcium chloride plus water plus carbon dioxide gas. So I have hydrogen, chlorine, calcium, carbon, and oxygen. Lots of elements involved in this reaction. So let's do my accounting. I have 1 hydrogen on the left and 2 on the right. I have 1 chlorine on the left and 2 on the right. I have 1 calcium on the left and 1 on the right. 1 carbon on the left and 1 on the right. 3 oxygens on the left, and 2 plus 1 is 3 on the right. So the calcium, carbon, and oxygen are all balanced in this one, but I need to balance the H and the Cl. And lo and behold, it's going to be very easy to do. All I need to do is put a 2 here, and voila, everything comes into balance. 22113 matches the 22113 over here. So sometimes a reaction that looks long and complicated can be balanced really easily. Let's do another example. In this example, calcium hydroxide, an aqueous solution, reacts with phosphoric acid to make water and calcium phosphate. So calcium phosphate is it has quite a few elements. It's got a polyatomic ion in it. And if I do my accounting here, I'm looking at calcium, oxygen, hydrogen, and phosphorus. So on the left side of the equation, I have 1 calcium, 2, I got to be careful here, 2 oxygens here, and then 4 here. So 2 plus 4 is 6 oxygens on the left. And then 2 hydrogens plus 3 is 5 hydrogens on the left, and 1 phosphorus. Now on the right side of the equation, I have 3 calciums. 2 times 4 is 8 plus 1 is 9 oxygens, and 2 hydrogens. I also have 2 phosphoruses because I have to distribute this 2 through everything in the parentheses. Wow, all right, so it looks to me like everything is out of whack here. I like to start with the most complicated species, so I'm going to start with the calcium phosphate because that is the most complicated molecule. I want to try to figure out what to do with it. I want to balance the calciums by putting a 3. So if I put a big 3 over here, let me do that in a different color so you can see it. Here's my big stoichiometric coefficient. That gives me 3 calciums. 2 times 3 is 6 oxygens plus 4. 6 plus 4 is 10 oxygens. And 2 times 3 is 6 hydrogens plus 3 is 9 hydrogens. And still 1 phosphorus. Okay, so now I need to figure out how to get 2 phosphoruses on the left side. Maybe I can do that by placing a big 2 here. That stoichiometric coefficient won't affect the calciums. I still have 3 calciums, but it'll give me 2 phosphoruses. And now I have, let's see, 2 times 3 is 6 hydrogens plus another 6, so I have 12 hydrogens. And 6 plus 8 is 14 oxygens. And I got that by distributing both of the numbers through the parentheses. Okay, so can I somehow do something with water to get the number of hydrogens and oxygens that I need? So I have 8 oxygens here, and 8 plus 6 is 14. So if I put a 6 here, will that solve my problem? 6 there gives me still 3 calciums and 2 phosphoruses, And now I have 6 oxygens plus 8 is 14 oxygens. And 6 times 2 is 12 hydrogens. I am finally in balance. So that problem was a matter of trial and error and guessing and checking, like all balancing equation problems is. Let's do another example. This one looks tricky. Silver nitrate plus sulfuric acid gives silver sulfate plus nitric acid. However, I want you to notice that the polyatomic ions are staying intact. So nitrate stays intact from left to right, and sulfate stays intact from left to right too. So really, all I need to look at is the sulfate as a group and the nitrate as a group. And if I do that, this problem becomes much easier than it might look on first appearance. I have 2 silvers on the right. So if I put a 2 here, that balances the silvers. And that creates 2 nitrates on the left. And if I put a 2 here, that makes 2 nitrates, NO3 minuses, on the right. And miraculously, that also brings the hydrogens into balance. So that looks like a very complicated one, but it actually turned out to be very simple to balance. So if you see that polyatomic ions are not breaking apart, you can kind of treat them as entities on both sides of the reaction.